Welcome to a lesson with Dr. Powell. Let's look at another example of verifying that a rigorous statement of a limit is accurate and true. For instance, what if we take the limit as x approaches, let's do as x approaches 1 of x squared is equal to 1. Okay, I mean, it's pretty clear that this is true using our limit techniques and just plugging it in, right? But let's verify the statement. Let's first write the statement down. Given epsilon greater than 0, there exists delta greater than 0, such that if the distance that x is from 1 is less than delta, then we know that the distance, the function, this time I'll just do the function, f of x minus what the output is, it's 1, okay, is going to be less than epsilon. Okay, so that's what we want to verify. We want to verify that this is true. So to verify it, remember, just means to find the delta that we're claiming exists, and then kind of point to an illustration of why this is true and call that a proof. Okay, so we just need to find the delta that'll work here. So we draw a picture. All right, let's just look at, okay, this part of the parabola here. Let's suppose it's this point that we're worried about, or that we're looking at. Okay, we have an epsilon going up here, an epsilon going down here. Then we want to figure out the delta that'll work, that pushes out in both directions. Now, issue here is the corner where we have an exit here is larger, or further away. The exit is further away from the center of the box that we want than this one. But we need to pick a delta that'll work. So we pick the smaller one. That means we're going to look at the exit on the right side, and that'll work. That's the biggest possible delta that'll work, and we'll use it. So we need to be able to figure out basically what that distance is for an arbitrary epsilon value up and down. Now, before we use just the slope idea, and here, well, the slope is variable and changing, at least of the tangent lines, it's changing up and down. So we can't use that idea necessarily, but instead, rather, we just compute it. We look at what this curve is. It's f of x is equal to x squared, and we think about what's going on. In fact, let's just name what different things are on in this picture. This line up here is y equals 1 plus epsilon. See why? Because we're going up epsilon from 1. Let's label what this x value is. This x value is equal to 1, because we're starting an x value 1, and the delta that we want is right here, delta, 1 plus delta. This is important because we're going to be looking at this coordinate point right here, and that's the point of concern or interest. And it would be nice if we could use this point to come up with an equation that relates epsilon and delta. Right now, we just wrote the x value in terms of delta. We wrote the y value in terms of epsilon. Now the question is, how do you relate this to this in an equation? The answer is a function, because a function relates the x value to the y value, right? With an equation right here. Y is equal to x squared. That's the relationship. We just put this for x, we put this for y, and we have an equation. We solve for delta. So looking at this, we're going to have y is 1 plus epsilon, and x is 1 plus delta quantity squared. And we just solve for delta. So we square root both sides, square root. Now, wait a minute. When you square root, there's a plus or minus going on. So let's think about that for a minute. Now, let's think about what this should be. Now, delta, we're going to imagine is very small, which means this side is going to be close to 1, which means it's going to be positive. So when we take a plus or minus square root, which one to pick? We're going to pick the positive one, because since we're thinking about a limit, we're thinking about how close we can get to things, to 1. So that'll actually tell us which square root to take. So we're going to take the positive square root and here. And now we can solve for delta. All right. So delta, okay, so delta is going to be, yeah, okay, that's right. So delta is going to be equal to, see, we got the square root of 1 plus epsilon, right? And then we just subtract 1 over. And there we go. That's it. We just did it. So we have found the delta that works. So let's just rewrite this, because a full part of verification is actually rewriting the statement down in the way illustrated in the last example. So instead of there exists delta greater than 0, we write let delta be something. Let delta be square root of quantity 1 plus epsilon minus 1. Then instead of saying such that, we say simply then if 0 is less, so what does this mean? Literally, this means the distance that x is from 1 is less than delta, which is right here in the picture. And we can even just draw an arrow over here. And basically to all of our work and say proof. Then if that's true, then that's true, because that's what we showed. When we showed the corner right there had that relationship between delta and epsilon, which we wrote right here. We actually showed that the box is contains the function completely, and the function's not outside of it. So that guarantees that the limit statement actually does hold. Thanks for watching.